nearest neighbor. And then I want to take that attribute, and whatever distance is returned from the nearest neighbor, I want to make that value p-scale. Okay, and then what happens is when it looks at these 2 points and it provides a distance, like this one's this nearest neighbor and this one's that nearest neighbor. So they'll both have the same distance. Okay, the distance is the full distance between the 2 points, but if I want half that distance to be the radius of my sphere, I go over here to the sphere and I just tell it to make the radius 0.5 units. The next thing that happens is the copy node resizes the spheres that are copied according to the p-scale value from the right side. So that's why they're larger and smaller. Now let's finish setting up this desktop before we go to part 2. There's a lot of panes here. This is just my scene view. This one I use for an overview at my SOP level. This one is a floating parameters pane, so whatever I click on that will follow. This one I set up to look at details. And I want to set this up, I want to go to this view and I want to click on my Voxhop because I always want to be looking at the details of this Voxhop. Okay? Then I'm going to go over here to the details pane and I'm going to just look at the p-scale attribute and I'm going to turn off that position information right now. So then we're going to dive down inside this Voxhop and we'll get started in part 2. Okay, so we're down inside this Voxhop. Now, first of all, what is Vops and what is a Voxhop? Well, Vops is just a context where you can create other operators. So you can make shaders in it for the shop context, you can make SOPs in it for the SOP context, you can make pops in it for the pop context, and it's just a tool building interface that kind of allows you to control at a little higher or lower level, depending on your perspective there. So what a Voxhop is a self-contained VOP network inside a SOP. And that's where I'm at here. You see, if I double click on this, I can go down inside. And here's the reason for the different desktop. In VOPs, you work horizontally, so you want a lot of horizontal real estate here. And by default, you have 2 nodes that fall in. There's a global variables and there's an output. And you have to have the output for the Voxhop to work, so be aware of that. Global variables, you can take a look. It's just a standard set. There's some things here like p-state or life. We don't have access to that because we don't have any attributes coming into this that are p-state or life. Okay, and you can check that again in the details pane. It's really handy when you start working with attributes. Okay, so before we get started with this whole process, let's talk a little bit about manipulating color. And I want to talk about hue, saturation, and value versus RGB. Now, RGB is just 3 floating point numbers, red, green, and a blue. And if you have 1 in any of those, you have full-on color. So RGB of 100 would be full red, 0 green, 0 blue. And just a note, we're working with the additive color model, so when you add light together, you get white, instead of adding pigment to get black, which is the subtractive model. So get that straight in your head first, okay? So, for example, if we look here at the CD, that's the surface color. It's this light color green, and that means it's a vector value, which in Vex speak is just 3 floating points. This can kind of get you in trouble because vectors and point values can have negative numbers and color is obviously only positive. So you have to be aware of that when you're plugging stuff in. But the idea here is that the color codes help you get stuff plugged in right. Light green for vectors, dark green for floats, blue for integers, and there's kind of an orange for string values as well. This is necessary because as you're getting down into this deeper context, it's kind of like programming where you have to declare variable types first. And this CVEX format helps you keep all that straight really easily. Okay, let's work with color. I want to break this CD vector value out into 3 floating point values. And we do that often with, there's a lot of adapter nodes here. And I'm just going to type in vector to float, drop that out. And you see that I can connect this up and it breaks out my colors here. This one would be red, this one would be green, and this one would be blue. And I can go over here to the other end and I can go float to vector and I can drop that in here and that would convert red, green, and blue back into this vector. So this is kind of how you get stuff in and get stuff out. Now I can just maybe affect the red channel or just affect the green channel. Okay, red, green, and blue is a pain in the ass to work with. It's native to the computer but hard for humans. For example, give me the RGB numbers for purple. Yeah, I can't do it either. There is a cool thing you can use though instead of RGB that's called HSV. So I'm going to drop in an HSV to RGB node and put it in here. And that means these inputs now will not be red, green, and blue. They will be HSV, or Hue, Saturation, and Value. And let's take a look at what that does. I'm going to middle click on this and I'm going to make a parameter for the saturation. Okay, it's called value 2. We'll scoot this over. Okay, and for its value I'm going to turn that to 1. So we have full saturation now. Push this back, maybe I'll push these over. There we go. And I'm going to do the same thing here. Create a parameter node. This is the value, or the black level, also called the luminance, also called the base multiplier, because all the colors get multiplied by this one. And when I put a 1 here, you see that I get red. Okay, I have full saturation and I can adjust that saturation right here. Okay, turn that back to 1. Here's my value. The first parameter, hue, is pretty interesting. If I make a parameter for that one, and I go here and I step through it, look what happens. I get a color shift. Okay, and this is just going around a color wheel. So for those of you that have never looked at a color wheel, here it is. And you see that we have red as a value of both 0 and 1. And typically when you encounter this, this is points on a compass, so 0 through 360 degrees. Except Houdini converts everything to a 0 to 1 range, which actually makes it really handy. So let me fix this so you can't cheat. Now tell me, what would green be in the Houdini range? And if you guessed 0.33, you would be right. Okay, so armed with this information, tell me what blue would be in the Houdini range. And yep, you probably picked it up. That's 0.66. So let's try that. Let's type in 0.66 here. Hey, look at that, I got blue. Okay? So now that you understand HSV, let me show you something cool. We can drop a random node in here. And I'm going to delete this out of the way. And we can take the point number and we can plug that in as our random seed. So it generates one random number for every point. And then we're just going to plug that in here. And because our number range is 0 to 1, we're going to get a random color for every point. Pretty cool, pretty easy, pretty powerful. Okay, a note on the random. This is called a deterministic random, which means if you're looking at this on your machine, you're seeing the same random colors I am, which is pretty interesting. That's not really random if that can happen. And it's a pseudo-random number that works the same way, like through every render pass and across every machine, which is a really handy thing as well. It means you can match stuff, even if you use a random number. There is a thing called a non-deterministic random here that gives you a pure random number. And you want to be careful with this guy because this can get you in trouble. Every time you change a parameter, for example, let me change this one, you're going to get a new random number. So it is truly random. Okay. So having looked at this, let's check one more thing out here. And that is, we know we have a p-scale, and I'm going to turn this CD off here. We added a color attribute now so we can see it. But we're going to turn that off. We're just going to look at this p-scale, and I can sort by p-scale or I can sort by point number. And we have a varying set of numbers there. Well, can I control color with that? And the answer is sure I can. I need to bring that in here first. And I can do that a couple of ways. I'm going to use the import attribute command, or node. And instead of CD, I'm just going to look at this value here, and I'm going to set this to p-scale. Okay, and I'm going to make sure it picks it in from the first op index. That's this one right here. I can set it to 1 and it'd pick it up from this input. Okay. And then I'm just going to plug this in. Well, actually I have to make it a float attribute first. Then we'll plug this in. And look, I'm changing the hues based on this p-scale. Okay, so now we're set up to kind of limit this color range a little bit, and we'll work on that in the next tutorial. So if you had trouble with the last bit or you just joined us, why don't you open file 05 p-scale HSV output. And it's a good idea to open anyway, just so we start in the same place. And one of the things I'm going to show you here is, just like we imported an attribute, we can export one. And we'll do that with the add attribute node. So I'm going to bring that down, and note that if I drop this value in here, I'm going to change this attribute name to test2. Bonk, look what appears over here. And you notice the numbers are exactly the same. That means it's adding a new attribute with the import attribute numbers. Okay? This is really handy. A lot of times I'll add an attribute just to test the output of something. I'll say, well, what is this value really? And I can take a look. You know, I can get information that way. So it's really handy to determine what numbers your nodes are actually returning. You can also do this with the print function. Okay, so you can set up this print, and I can take this number and plug it into the print. And if I click output text to console, I get a console here with those numbers. Okay, this is handy in the shader context, and we'll use it once in this context as well, because you can't actually add an attribute that you can see at the shop level. But when I'm working with geometry, I like this add attribute. It's a lot simpler. And you know, after I use this, sometimes I'll just blow it away, and I won't use it anymore. Also note, if you're working on Linux, the print node won't work unless you launch from the command line. Then it'll bring up the console, and then this print node will work. So I want to limit these colors. And there's a bunch of possible ways I could do that. I could put in a bunch of if-then statements for every color, but that's not very procedural because I need a separate if for every color that I wanted to change it to. And I want to be able to change this on the fly. I want to be able to do 4 colors, 6 colors, whatever. So how would I approach this? Well, it'd be nice if I could just kind of round these all off, if I could kind of condense them somehow. And if I try bringing a round to integer value, and I put this in line, look what I'm going to get. All red. Well, why is that? Let's do the add attribute trick. Plug this in. This will be called test. And you'll see that my value is all 0. And that's because all these numbers, none of them are above 0.5, so none of them are actually going to get rounded to 1. Okay, so you know, on a calculator, sometimes you can say, okay, round to 2 decimal points. What is the mathematical process that's actually going on there? How is that working? That's actually pretty simple. What you do is you multiply this number by, we're going to create a parameter node here. I middle clicked on that to get this parameter. And this is going to be called, let's get this over for a sec. I'm going to call this num color for the variable name, and for the parameter that my users are going to see, I'm going to call it number of colors. Okay. And I'm going to set this value first to 100. Okay, now we'll scooch this back over. And, whoops. And look at our test values now. Okay, I rounded it first. I don't want to round that. I'm just going to multiply this straight. So I moved the decimal place 2 points, right? By multiplying it by 100. Now I have values that I can round if there's an integer. So I'm going to drop this in here. There we go. And you can see I rounded those off. Okay, these aren't usable numbers though, because I need them back into this 0 to 1 number range. But I can divide by that same value that I multiplied by, and it'll move that decimal place 2 points the other way. So now I have limited these rather high precision numbers to only 100 possible values. Do you see that? Do you see that there's only 100 possible values here? Okay. What happens if I change this value to 10? Now I've limited it to only 10 values. What happens if I limit this to 3? Now there's only 3 possible values. Okay, let's see if that works when I plug this in down here in my hue. Yeah, except I got 2 values, not 3. Why do I only have 2 values? Well, I think it probably just has to do with the distribution of these numbers. You know, if the numbers I have in my initial range, like I said before, don't go to 0.5 yet, and I am working here, I'm expecting a 0 to 1 range. So in signal processing terms, what's going on is there's too much headroom in this system. I'm only here from like 0.1 approximately to 0.4 approximately, and I have, you know, only 40% of my number range used. So I need to expand this. And we're going to take a look at this process of expanding this headroom in the next section. Okay, so in part 4, the first thing I want you to do is open up the file 06limitcolors.hip, and that'll get us all on the same page so we can start this together. Okay, if you take a look, this is exactly what we did last time. We're importing this p-scale attribute. We're limiting the precision right here with this multiply, round, and divide range, and we have this node that's called number of colors. If I go up here and I click on the Voxhop, you'll see that I have component 2, and number of colors. Those are from the saturation and value nodes being named component 2. If I call this one saturation, okay, and if I call this one value, you'll see that when I click on this node, those names change. Okay, so this is, those parameter nodes again are building that interface. And this is a good time to note that the convention currently in Houdini is to color those inputs yellow. So when you're looking at somebody else's file, you can tell that, okay, those are my parameter nodes because they're yellow. We also have this add attribute called test. It's our test point. It brings this information in over here in our details view. And from here, we're going to start looking at this problem of headroom. So we want to increase this range instead of 0.9 to 0.38 to 0 to 1, so that we'll have a full range of colors over here. And some of you are already going, fit range, and that's exactly right. We're going to drop a fit range in here. Okay. Now the problem with the fit range is I need to adjust the source min and source max. And my source min I can get away with 0.1, and the source max, let's put in here 0.4. Da-da-da, and hey, look what happens. We get 3 colors in our view, which is pretty cool. But this is a pain in the ass because I got to come in here and type this in every time. I don't want to do that. I have a computer. This should figure this stuff out for me. And the other thing is, if I have a user that doesn't know anything about Houdini, I want to be able to just hand this node off to them, have them move the knobs, and come up with a working solution. I don't want them to have to go search for these minimum and maximum values and input this data. I want this to be automatic. So how would I go about doing that? Well, as a human, you know, I tell the machine to sort by these scales, and then I look and I find the lowest and I find the largest, and that's how I know how to type these variables in. I can't really break that down into steps for a computer, so what process could I tell the computer to make this work? And I think the computer could probably compare every number against every number and find a minimum and a maximum. And in fact, there is a minimum and a maximum, and you can put more than one input in there and it will output, this one will output the minimum, this one will output the maximum. So I'm set to do that. So if I bring in this import attribute and I take the minimum values and I take the maximum values out, what do I get? Let's get that test node over here. Bing. Okay, it's saying it doesn't work because it needs another input. The minimum of any one thing is one thing. Well, let me copy this and I'll put this down here. We're going to import that same attribute again and we'll use that as the second input for both of these. And you're like, Dave, that doesn't work. You're comparing the same thing with the same thing. And I say, yeah, that's right. But look at this. There is a place in here to input a point number and select the attribute for a specific point. So I'm going to use that. And this point number to point number connection is assumed. Okay, another handy thing about VOPs. Anytime you have one of these global variables and you have the same variable as an input in a node, that connection is assumed. Okay, but for this one I can break that connection and I can put an add in here and I can offset this point number. So for example, I'm just going to put a constant node in here. And I'm going to adjust the value of this constant node. And you see that my numbers change over here because I'm offsetting these values. Okay? So now, for example, this one is comparing, move this over here. This one is taking the minimum value and it's comparing the p-scale of 0.0 from import attribute number 1 with the p-scale attribute from import attribute number 2 of whatever point is put into this point number value. So right here, in this case, it's 4. So if I just stepped through and I compared every one of these with every other one, I should get reliable minimum and maximum values. And that is what a loop is for. So in the next section, we're going to look at how to make a loop in Houdini and how to incorporate this idea in the loop. Okay, hi, this is part 5. We're going to talk about loops, and I want you to open the file 08 loop workflow with attribute outs.hip. That's a mouthful. Okay. And it will bring this up. Now, this is what we did last time with a couple of exceptions. First of all, I added this parameter node, and I called it attribute name. So at the operator level, you can input the p-scale attribute or whatever attribute you choose, and it will control the name for both these nodes. Okay, that lets the user pick the attribute instead of having us pick the attribute. Okay, the rest is the same, except I have two more nodes over here for test points. I have a min and a max, and I also dropped this for loop in here that you can get from just typing for. Okay, we're going to try to make a loop, and we're going to try to make this work. So the first thing to note is the for loop is a subnet, and it's got inputs and outputs. And what I want to do is I want to copy this stuff right here, this min and max, these four nodes. I want to actually cut those, Control X, and I'm going to drop down inside the for loop and I'm going to paste those. Okay, now I get some error messages because some stuff just isn't hooked up. Okay, let's take a look. I'm importing this attribute string variable and I'm plugging that in there, which is good. So I'm going to go inside and I'm going to make sure that this gets connected. Dink, dink. Okay, and I can plug these out if I want. Next and next. Okay, and the reason I'm getting errors here is these data types aren't right. So we'll plug these in and everything should be green. There we go. Just a note on data types. If you try to plug a string variable into a float, it doesn't work, and it'll tell you so. And a lot of times when you plug something like, for example, I plug an integer into the float, you'll get, sometimes this node will change to accept that, or sometimes you'll get a dashed line, which indicates that there's an error someplace. So be aware of those errors. Let's see, let me make one here. Okay, we'll plug this into here. You see that dashed line? That indicates that, hey, I'm trying to plug a float or a vector into a float, and it just doesn't work. Okay, and this one will probably actually pick just the X value there. Okay, so we're dropping down inside this for loop. Now we modified the point number for one of these last time. We need to do that this time as well. So what I'm going to do is I'm going to grab this global variables and I'm going to grab the point number and plug it into the next parameter. Okay, now note there's an I and an end. These are important. The I is this iteration of the loop. The end is when to stop doing the loop. Well, we need to tell it to use the number of points value and stop when you get to that point. Okay, we can control the iteration of the loop if you want, but if you don't, it'll just run 1 through the end, or 0 through the end, actually. So we'll just leave that. Now we'll go inside. And we're going to plug the point number value into this one, and we're going to plug the iteration value into this one. And we're going to get some numbers. Now it looks like our max is working over here, because our maximum value is 0.386, and that's what we get for our maximum. But our minimum is not working at all. And gee, what's going on there? Well, in fact, the whole loop isn't working, because you'll notice that we're actually not sorted by p-scale, we're sorted by point number. So the last maximum value it sees is 0.38, which happens to be that one. The last minimum value it sees is, let's get over here, min value is 0.15. The last minimum value it sees is 0.15. So you see that's where the min kind of gets screwed up. And what's going on is it's just comparing two numbers at a time and outputting the minimum of those two. It doesn't do a cumulative of all the numbers it's seen. So we need to make some kind of memory. We need to pass some data out of this loop and bring it back into the loop next time. And that's actually pretty easily done. What we'll do here is we'll go up to this level, and I'm going to drop a parameter node. Sorry, I'm going to drop a constant node in here. Okay, and this one we're going to call min accum, and then we're going to copy this, and we're going to call this max accum. Okay, now you want to be careful when you copy nodes, because the name of the node becomes the variable that's used in Vex. So you don't want them to ever be the same. And if you drop a parameter or a constant down and they have the same name, it's going to gray one out. It's not going to use the second instance. So we're going to do a handy little trick. We're going to type in $OS here. And that just says pick the name of the node. So we'll do that for both of these. $OS. And if I would have done this in the first place, I could have just copied this and pasted it, changed the name, and the variable name would have changed as well. Because you don't see constant nodes, I'm not even going to mess with the label. I'm just going to leave that the same. Okay, so I have these two values. I'm going to plug these into the loop. And you'll notice when we go back down inside that we have these two outputs that are labeled the same as the inputs. Well, that is not coincidental, because what happens when I plug these outputs in, it's going to take this value of the minicum and it's going to place that in that constant node and bring it in again next time around. So we can just take these values and add these to our min and max operations, and we should get decent numbers. Oops, I did something wrong. Minicum there. Okay, here's what the problem is. Okay, now look, our max is definitely working. Our min, not so much again. Uh-oh, what's wrong here? Well, the first time through the loop, the value that gets used in these constant nodes is the value that's set by default. Now for max, that value is 0, and immediately the next p-scale number is larger, so that works. However, the min gets set to 0 too, and anything compared with 0, unless it's negative, becomes 0 again. So we need to fix this initial value, and if we set that to 1, look at that. We have our exact min and our exact max, which is pretty darn cool. Okay, in the next lesson, we're going to apply this to the fit range and finish this up. Okay, the first thing I want you to do here is open file 12 forloopcomplete.hip. So we all start in the same place. And we'll take a look. Our minimum and max values are working. We've derived those from this for loop. Okay. And we have the rest of our piece more or less working. What we want to do is modify this fit range so we don't have to type in these numbers by hand. And that's pretty easy. I have a min and a max value, right? So I'm just going to plug this into the source min. And I'm going to plug this one into the source max. Dink. And yay, it works. It works, it works, it works. But look, there's an issue here. The largest sphere is red and the smallest spheres are red. So we only have 3 colors, but there's some weirdness going on. What's that about? Well, I'm going to put in another test node. Add attribute. We're going to call this one test 3. And it's going to be a float. And we're going to pull that in here at the end of my divide, and I'm going to see what's really going on with this number system. Okay, I have values that range from 0, 0.3, 0.6, and 1. That's actually 4 values. Oh yeah, it's using 0 first, and then it's getting 3 values plus 0. And remember when I was talking about hue saturation and value, 0 and 1 are both the same point on that color wheel. So that's the reason that our size 1 and our size 0 balls have the same color. I wonder if we could fix that. Well, we could do this by eliminating the 0 value or by eliminating the 1 value. And I think I want to eliminate the 1 value because I like to always start at 0. So how am I going to do that? If I made this 1 value 0.667, or if I just modified my fit range over here to only output a maximum of 0.667, that would be really cool. And I do have this destination max number. Can I do that? 0.667. Yeah, I can, and that would fix this situation. Okay, so how can I do that? If I take this number of colors and I divide 1 by that, so I'm going to put in a constant, and I'm going to call this 1, and we're going to make the value 1, and I put a divide node in there. Divide that by my number of colors. Take my test node and take a look at what that gives me. That gives me 0.3. Well, 0.3 is my building block, right? In these, if I reconnect this here, I have multiples of 0.3 from my values. So that's a handy thing to have. And the tallest number is just 1 minus that building block. And if we're using real math terms, we can say 1 minus that unit value. So I can go subtract, and I can subtract this number from 1, and that gives me 0.667, which is what I want for my top value. Then I'm going to put a null in here. Just because I can carry this around better with a null. Makes things a little bit neater sometimes. And I'm going to plug that into my destination max. Dink. And there we go. 3 colors distributed on the points. Let's see if it works. Let's go up 1 level. Click on my Voxhop. And I'm going to change my number of colors here to 4, 5, 6. Sure does. Okay. Let's make sure it's procedural. Let's change the scatter points. Number of points. 11, 12. Yep, seems to be working. Change the random seed. Yep, also seems to be working. Going to go back down inside and just double check my headroom here with my test node. Sort this and see that I have a range from 0 to 0.833. You have to go up 1 level. Number of colors 3. Go back down inside. And my test 3 values look good. 0 to 0.667. That's exactly what I want. To get started, open the file 15 fitRangeWithDetailAttributes.hip. Okay, for the last section, I want to show you something interesting. The loop we created in Vops is actually kind of inefficient, and that's because it has to loop through all the iterations of all the points to find its value. And there's a quicker, easier, more efficient way to do that in Houdini, and that's by using detail attributes. Now, detail attributes are kind of interesting. I didn't see a use for them for the longest time, but now I have some better insight and I see that they're actually super useful. So let's first define a detail attribute. If I put down an attribute create and I plug this in and I make this guy a detail attribute. Okay, so if I look at that detail attribute, it's a single value. And that's the way detail attributes work. They're a single value for all the points in a set, which lends itself very well to our application because we're looking for a single minimum and a single maximum value for all our p-scale point attributes. So if I name this one, let's go back to attribute. I'm going to say p-scale max. I can get a single value for all those. But I don't want to create a new attribute. I want to actually promote an existing one. And the existing one is p-scale. It's a point attribute. I want to move it to a detail attribute. And the promotion method, now this is where it gets interesting. I don't want to average. I want to choose the maximum. And we'll find this value of 524. Okay? I want to change it to a new name. I want to call it p-scale max. Okay, and I don't want to delete the original. I want to keep that because I'm going to do the exact same thing again. And the new attribute I put in from p-scale to a detail is going to use the minimum method, and it's going to be called, yep, you guessed it, p-scale min. And I don't want to delete the original there either. So let's look. 0.5247 0.1069. If I go back to the point attributes and I sort 1069 is my minimum, 0.5247 is my maximum. Okay, so those appear to be working. Let's see how we get those into Vops. If I use an import attribute and I put this p-scale max in there, and I hook it up to our test node, and it's actually a float, I get nothing. I get problems. And that's because the import attribute node only pulls in point attributes. What I need to do is drop a parameter tab down there. And I can call this p-scale max. And then we'll use the $OS shorthand to bring in this name. Now let's take a look and see what I get. Yep, there's my value. Okay, so to import those detail attributes, you have to use a parameter node. That's the only one you can use. Okay, so I have a max value, and I'm going to copy this. And instead of p-scale max, this is going to be p-scale min. Okay, and we'll hook this up to make sure we're getting decent values there. Yep, that's working. Okay, so I'm just going to put those into my fit range. Source min, source max. Take the output of this, and notice that our p-scale normal value now will return 1 for the largest value and 0 for the smallest. And this is super quick. This just flies. It's way quicker than our loop. So I hope this is interesting to you, and I hope you can find uses for this. And I wish you happy creating with Houdini.
Hi there, and welcome to Introduction to Variables and Expressions in Houdini. Over the next several lessons, I want to really start delving into some of the more technical aspects of Houdini, which is just passing information around from the various networks and being able to really drive whatever effect that you want. Expressions are to some scary, but to most, they're not that bad. And I'm sure you'll find that once you start getting into it, it's really going to become a very important tool in your arsenal. So let's get started here. I'm going to quickly put down a sphere, and I just control clicked on that, and immediately we get all our parameters up here. Now, expressions is basically any sort of information that you are going to fill in here. If you leave it as just a blank number, that's fine, but a lot of the time you want to start driving stuff around. So let's just quickly put some keyframe animation onto this uniform scale. If we Alt left click on that, we set a keyframe, and we can go forward a few frames, middle mouse button, and drag this, set another key, go forward some more frames, get a new value, set a key, and that's all we're going to do for now. So if we take a look at this, you can left click on uniform scale. You see that this parameter is green, and when we left click, it changes what we're viewing here. And that's the same as if we were to go to this right click menu and go into expression and toggle the expression. And what that's giving us is this is going to return us the exact values per frame, but this is going to tell us what we're doing to achieve that value. And right now we're using a Bezier function. Anytime we use expressions in Houdini, almost at any time that we're using expressions, we end up using functions. And it's just going to be a line of text with brackets, and almost always there's going to be information inside these brackets as well. So I'm just going to shift middle click, and this is going to bring up our channel editor. And so we've got our channel editor open here, and if we just press space H, we can hone in on this, and we see this animation curve that we've got here. And if we select this curve, down at the bottom you see the word function, Bezier. And if we click this, there's all sorts of different functions that we can use for animation. We can use a constant, which is going to just flatline us here from value to value, or a linear, which will give us a straight line, and of course there's all sorts of other ones we use here. Now that's all well good for keyframe animation, but a lot of the time in visual effects you're going to be working with large data sets of particles or fluids or whatnot, and keyframe animation starts to get a little bit difficult to use because there just ends up being so much information going through your system. So we tend to want to drive a lot of stuff using expressions. So let's start looking a little bit more in depth at that. Now, right now we set keyframes on this uniform scale, which is a single parameter. Now there's 4 different types of parameters that we need to really worry about in Houdini. This is a float. Float is just a single number. It can be an integer or a number with decimals. It's just a single value. So like an alpha attribute, for example, would be float. Up above here we've got this translate, rotate, scale, pivot, and you can see that each one of these parameters has a group of 3 values, and that's because it's a vector. So anytime that you see a parameter that's got a vector, that again is going to have 3 values, and this type of data is usually used for point positions or directions on normals, or colors as far as RGB or HSV, and even like velocity attributes for motion blur. There's another type of data that we're not going to bother getting into in this tutorial series because it starts getting a little bit more intermediate or complex, advanced, and that's the concept of a matrix. A matrix is going to be a group of 16 floating point values, and so, like I said, we're not going to get into that because it's really just a little bit more advanced than we need to take this. Now the last type of data, if I'm just going to delete this, and I'm going to put down a font sop. Now we'll see here that there is text that gets put down here that says frame 22. And if we dive inside this object, just double click, we see a couple of different parameters here. This one, font, tells us which font we're using, and well, that's text. And the same here down under text, we get frame. We also get this little yellow snippet of text. We'll talk a little bit more about why that's yellow later. But right now, this is text, and so anytime you see text as a parameter value, that means that it's a string, which is very handy in situations like this when you want to have text in your viewport. What you will notice is that if we come in here and we put 1 plus 1, for example, that's literally what we get, is 1 plus 1, which what we're going to start talking about now is that we can actually drive stuff around using simple math. And in the case of a string, that's not going to work out so well for us because it is text. So if we were to go over here to our translate, for example, you could do 1 plus 1, and you see that we've got our color here again. We can left click on this, and we see that this is our expression, and this is the result too. It's actually doing some math for us. If we want to get math to work for us inside a text field, we actually need to start telling this to evaluate and not just be text, but to be an expression. So we can actually use the backtick key for that. It's right next to the 1 button on the keyboard. And if we type that, then all of a sudden this starts evaluating and give us a value of 2. And so there's all sorts of different math equations that we can use. Obviously, we can use addition, or we can use subtraction. We can use multiplication. So if I just say 5 times 3 maybe, then we get 15. You can also do division. Just use the slash key. And you can also do a form of division called modulo, which is you may be familiar with it as a percent sign, and it basically does division and returns the remainder. We can also do exponential stuff, so if you use the caret, we've got that. And you can also do exponent stuff in the sense of adding 10 digits on there, so we've added 3 zeros, or we can move 3 digits away from the decimal point if we subtract, so the E becomes very useful for that. And of course you can also start getting into order of operations by using brackets. So our main tools for doing math are the brackets E, caret, multiplication, division, modulo, addition, and subtraction. And we get nothing there because we're telling it to evaluate, but if we put it as a string, these here are really the symbols that are very useful for us for simple math. We can also start getting into comparisons, very simple comparisons. You may be familiar with the greater than or less than symbols from math. You can also do greater than equal to, or not equal to. And so there's various combinations of stuff that you can do for that, and that starts getting very handy because in certain situations down the road, I'm just going to quickly set this into creating context, and so I'll put down a sphere and a tube, and you can see now that we get these two objects here inside the same geometry node. And so what I'm going to do now is I'm going to simply put down a switch node. And this is purely for demonstration purposes, but there's all sorts of situations where you would want to do something like this. As I mentioned before with that font sop, let me just quickly put that back down. If we have a font node here, we see these little yellow text here that's the $F, and what that is that is a variable. It is it's a little alias that we have that'll bring up a number associated with this text, and so this is bringing in our frames. So you can see we're at frame 34 and it says 34 up there. So what we can do is we can start using data such as this, the variables, along with our other expressions to start really driving stuff. So for example, if we want it to do $f is greater than 1, then we can now say that whenever our frame is greater than 1, return a value of true, or 1. Whereas if it's not greater than 1, then return a value of 0. The expression evaluates to false or true. And you can see that in the case of a switch here, this is going to control 0 and 1 is our two inputs here. So you can easily switch between stuff on a certain frame. So that gets to be very useful in all sorts of situations. And so there's all sorts of various situations or various comparisons that you can do. You can do or and statements as well. So if we say if f is greater than 1, or if f is less than 10, then we evaluate true. So even on the first frame now, it's going to evaluate true. So this is always going to evaluate to true. But if we said something like this, if we switch that to an or statement to an and statement, both of these statements must now be true in order for our statement to evaluate to true. So at frame 1, it's false. Frame 2, it's true. All the way up until frame 9, when it's at the last point, but when it's less than frame 10. Once it reaches frame 10, then it's going to be false again. So simple comparisons, simple math, and that's where we start. So in the next tutorial, we are going to start getting into the concept of environment variables. Welcome back. In this lesson we're going to discuss environment variables. Now in the previous lesson we saw with using this Voxhop font node that we had this yellow bit of text here with the $F that called up information whenever this is called. We can actually use this type of information in all sorts of places. Whenever we see that $, it lets us know that we're using a variable. So if we go back up to the object level here, I'm just going to start going into our file and decide where we're going to save this. And this is where we're going to start coming into environment variables. You can see up here that we're looking in $hip. Now right now this file hasn't been saved anywhere, so it's going to try saving it in our default directory. You can also go to our home folder, which is a variable that you can set up. That'll depend widely on which operating system you're using. We can also go into our desktop or $job, and that's where it's going to try saving stuff by default. If we go to our desktop, I'm just going to go into this folder that I created and overwrite this file that exists. Now what we can see is that whenever I go back into this type of menu, if I were to go to $hip, because we are now working with a saved file on disk, it will try to, when you click on $hip, it will go to the folder that that file exists in, and it'll work relative to that folder. It's very useful, and you'll notice that we do that a lot in the side effects files because it ensures that as you pass files around from operating system to operating system, or even just computer to computer, that everything is able to maintain its paths and hook up nicely. This is useful obviously with texture maps and cache geometry. So let's just cancel that, and let's just start up a very basic simulation here. If I put down a tube, we will come in here and we'll just change the height. I'll give that a value of 3 maybe. And then while I'm here at the object level, let's just translate this and rotate it. And now I'm going to add a point constraint in. I'm going to turn this into a rigid body object. So if we come up here to the shelf, we can turn this into a rigid body object, selected in, there we go. And now I will also just put down a point constraint. So we've got that, and so we've got our object selected. You can see down here in the help that it, at the bottom in this area, that it prompts you to select something, and then press enter. Done. And now it's asking us to place this point. We could just press enter to do it at the origin, and then control it using the handle. So now we've just got a very simple simulation of this thing, just swings back and forth. Very simple. And we'll put down a sphere. We'll raise this up, and we're actually going to turn this into a particle fluid object. So particle fluid object. Done. And I'm just going to quickly go into the simulation here and press L to organize this. And I'm just going to quickly reduce the quality of this simulation. Right now we've got a particle separation of 0.1. Let's just set it to 2. And that should be fine for our purposes. One thing that's handy to do with particle fluids is to just give it a bit of jitter scale. So I'm just going to do that. We've now got some jitter. And so now if I press play, we should have this simulation comes down, and we get a bit of interaction here between those two items. So I'll just quickly go back up, and I'm just going to raise this sphere up just a tiny bit more, just so that we get more of an interaction. And that should give us what we need. So the next variable that we're going to do is we're going to start caching this out to disk. So if we navigate over to our out directory, we can put down a geometry ROP. And this of course allows us to cache stuff to disk. You can see that we are using $hip to save relative to where our file is saved, and also $F so that we get our frame numbers. We can also do a little bit of frame padding by using a number after the $F, but we'll just leave that for the time being. So if we open this, like I said, $hip, we're just going to create a new folder and call it BGO, go in here, and we'll save it like this. What we're going to do now is we're going to use another variable, which is $hip name, and that will allow us to use the name of your hip file in the your file names, and that can be very useful, especially you'll see in a bit when we're going to do a wedge. It can help to use your hip name inside your sequence, because as you start saving out multiple files later on, it's handy to know which file it was that generated your cache geometry. So $hip name, you can see, gives us another variable that will save out our variables underscore example dot hip. Okay, and so the next step that we're going to do here is we're going to use a technique called wedging, which is very, very handy. So if you just quickly go to the side effects website here, you can go into the learning section under tutorials, click on rendering, and you'll see the tutorial that has already been released for the wedge drop. So if you're not particularly familiar with this and you want to learn a little bit more, it's a very, very handy tool and very worth taking that extra few minutes to look into. But basically what a wedge drop does is it allows us to do multiple iterations or multiple tests on something and get it very quickly. So I'm just going to delete this prefix that ends up going into the file name. The wedge drop has its own global variable called $wedge. So what we can do now is we can add a wedge parameter, and we need to find out what the channel is that we're going to wedge. So in this particular case, I made mention, if we go back here into our Autodop network, that it's very handy using particle fluids to use this jitter stuff. And as we use jitter scale, or jitter seed rather, you can see that each of these will place these particles in a completely different default location. So it can be very handy to generate particles, do a simulation, change the seed, do another simulation, change the seed, do another simulation, etc. And by doing that, you can get large numbers of particles, get essentially a high-res simulation, but it takes a lot less effort for your computer to do multiple small ones than it does for it to do a single large one. So this is what we're going to wedge. So if we copy this parameter, right-click, copy parameter, and go back to our out network into our wedge drop, we can just right-click on this, and we can go to paste copied relative reference. Now what this does is it places down a function for us, an expression, and we actually don't want to use that in this particular scenario, so we're just going to delete this out. So I'm just going to delete the stuff that we don't need here, and we'll just leave it as a string that goes directly to our channel. So we're going to wedge this parameter. What we can do is we can say, instead of using random samples, we know that we are going to do this 4 times. So we'll do 4 steps, and we'll give it 3 different integer values, 0, 1, 2, 3. So we want it to go from 0 to 3. We can also just make sure that we give a name up here. So just copy your jitter seed and paste it over here, Control-C, Control-V, and enter. And that's most of our work for us. So now what we can do is we can go back to our geometry ROP, and we can add in another variable. We can add $wedge in here, and this will kick into effect as soon as we start using the wedge ROP. So if we press enter, we can just quickly tell this to do a frame range of frame 1 to 120, and that should be it. So now we go back to our wedge drop. And there's 2 things that we need to do. We just need to make sure that we've got the output driver connected, so you can drag this node up here, let go, and then we click render. And so when we render this, you see that we actually got a small error down here, and that is because I forgot to do one small thing. In the geometry ROP, it has no idea what it is that we're trying to cache out. We've quickly just got to go up to the SOP path and connect this to our sphere fluid object. So to figure out which one it is, we just need to select that. I'm quickly just going to accept this, and then I just want to confirm that this is in fact the node that we want. So if we click this arrow, we'll see here that we've got our particles which feed into our particle fluid surface. So yes, this is the node that we want. So if we come back and we render this now, this should work. And so what you'll see happen here is this will come through and it will do the simulation once. And I'm just going to let this go through. It's a fairly quick simulation. And after it finishes the simulation once, it's going to go back through and it's going to do the simulation again. And then it'll go through and it'll do the simulation again, depending on however many steps that you tell the wedge drop to do. And so you can see that it's restarted there. And now I'm just going to pause the video. Alright, so now that we've got this all cached out, we can just go back into our object, into our sphere object fluid, and right now we're reading stuff live from a simulation. And I'm just going to quickly turn this off, hide other objects. And so this is going live from a simulation, but we don't actually want to do that. We just cache stuff out to disk, and so that's what we want to read back in. So we can put down a tab and put down a file node. And if we've done some demos in the past and ended up overwriting the default geometry file, it looks like. But anyway, if we come in here, we can choose geometry, and it's by default going to come back into this $hip/bgo because that's the last folder we were in. And you can see that we've got this stuff written out to disk. You can show sequences as one entry, and it'll show you each individual file that we've written out. But generally, you're probably going to want to have this show sequences as one entry. So we can select this and accept, and you can see again we're using $hip and $f. And what we're going to do here is we're going to simplify this considerably so that we can get some nice behavior whenever we copy and paste this node. So if I come up here and select this whole section right here, Control C, I'm actually going to give that name to the file node down here, Control V. And so you can paste that down here. You could have just as easily pasted it up here. But the point is now that we've got our node named this, we can actually use the $OS, our operator string, to overwrite this part of our file path. So $OS. And you can see that that still works up here to load in our geometry. But the advantage to doing this is in Houdini, whenever you copy and paste a node, the number that's at the end automatically will increment. And if you pay attention up here in the viewport, as we paste in each node here, you can see that this was actually updating and giving us our different sequences that we wedged out. So if you pay special attention to your file names and whatnot when you're working, it can actually be a big time saver to use different variables. Because, as I was saying, we actually want it to merge this stuff together and have various low-res stuff all linked together into one node. And that's exactly what we now have. So variables get to be very handy. The same way that we've got the $wedge, we've also got the ability to use if you're familiar with takes, you can also use a $active take to write out the name of your take into your either your images or BGS as you're caching those out. And if you're not familiar with takes, if you return back to the side effects website and actually go into the Houdini 8 tutorials, there's the render pass workflow right here is an excellent tutorial to go through, and you'll really be able to use yet another tool in your workflow. Hi there. In this lesson we're going to discuss Playbar Variables. Now we've already started to take a look at this in the past with $f, which if you put down a font stop here, by default we have $f is being used as a variable. Now that is our frame number. And so if I start scrubbing through here, you'll see that that updates to whatever frame we have down here is the same thing that will get viewed up in the viewport there. And so there's also a couple of other very useful ones that we want to get into. But before I get into that, you may be familiar in other packages with the concept of frame padding. And that's very useful because a lot of the time in compositors and stuff, you want to have a nice sequence where it's always got a 0 in front, so that it's always going to be 0, 1, 0, 2, 0, 3. Always going to have two digits here. So the way that you can do frame padding is to simply add a number onto the end of your $F. So by adding this 2, you can see that we now get these zeros on here. Or you could say 3, or you could even say 30. Whatever the padding is that you want to use, you can simply add it on using the $F. Now that becomes a little bit more unwieldy as you start doing complex math stuff down the road, and we'll look at that in just a little bit. So we've got $F, but we've also got some other options. We have one called $FF, which, as you can see here, this is still not doing anything different. But that's because we are using integer frame values. It's always going to 5 to 6. We're not going between frames. If we come over here to the global animation options, we can click that and bring it up here, and there's a couple of different options here that we need to pay attention to. One is, as I said, the integer frame values, and if I turn that off, as I start scrubbing through here, you'll see that we are able to go to non-integer frames, like between frames, and so that's what the $FF does. Otherwise, if we just had it at $F, it would round it to our nearest value. Okay, so $FF becomes very useful when you start working with particle simulations and whatnot, because a lot of the time you need to start doing sub-stepping to make your simulation more accurate. So we have $FF, and there's also going to be variables where you want to work in units of time. Whenever you see units in time, it's going to be $T that you want to use. Because again, it's going to update between frames and on every frame, and it's going to be in units of seconds. So if I just go back to integer frame values again, you can see that this doesn't reach a value of 1 until we get to frame 25. And that's because we've got 24 frames per second. So on frame 1, we start with a value of 0. It's the 0th second. And after 24 frames have passed, we've got 1 second. And after 24 more frames have passed, we've got 2 seconds, etc., etc. So $T is units of seconds. There are going to be times where there will be parameters that expect units of seconds, and you'll want to be able to key it on and off on a given frame. Now the way that we can do that, if we just quickly duplicate this object here, and maybe move it down, merge them together so that we can see these both at the same time. There's a very simple equation that we can use to get frames and seconds. So right now we're going to turn this one into an equation. So we'll put this in backticks so that we know that we need to evaluate whatever math we stick in there. And we're going to change this back to $F. And we're going to put this in brackets and divide by the frames per second. And this would normally give you what you'd expect. This is going to give you frames per second, which is going to equate into time, units of seconds. But the one thing to be aware of with this is that in Houdini we always start on frame 1, not frame 0, whereas our time starts on 0, not 0.41667. So whenever you're trying to work out with an equation like this, you just want to subtract 1. And now you can see that this equation here is the equivalent of $T. As we go through here, these will always give identical values. Okay, so that's just a very short equation that you need to be aware of, and we'll make some better use of that in a little bit. So $F, $FPS, which is your frames per second, that's this right here. We can also change this to a 30, and you'll see that our time stays the same. And that's because we are always using seconds here. But you will also notice that we've got 30 seconds here. So 30 versus 24. And so one thing that you may actually be a little bit confused about is as we were changing the frames per second here from 30 to 24, you see here that this keeps changing. What you need to be aware of is that the time code down here at the bottom, as you update your frame range, this always updates to whatever the equivalent time would be. Okay. So now that we've got that done, let's just quickly build up a simple particle simulation. So we can go back up to the object level and delete this object. And I'm going to put down a sphere, control click on that, and I'm just going to do some very quick simple simulation here. So let's just give ourselves, I don't know, 55 frames of animation to work with. And on frame 1, we will just lift this up, Alt left click, frame 48, we can go over here and Alt left click again. And somewhere in the middle here, we'll just drop this down like so. And so now we've got some very simple animation of this sphere that just goes through like that. We'll just turn on real-time mode. And there we have it. So that's some very simple animation that we have there. We'll just leave it as is. You can see that that's using the Bezier functions. And if we come up to the Create Particle tab here, Create Particles, we'll just turn this, we'll source some new particles from this geometry. So we click on that and it builds us a particle network over here. So there's a couple things that we can do on this. The first thing is, let's say that we do not want our particles to be emitting all the way through here. Let's say that we want to wait until it's at the bottom here, frame 25, and then the particles start. There's one way that we can do that is on the pop net itself. We can go back here, go into our particle emitter, and on the pop net itself here, we can just put a condition on here. So the start time, as I said, this is looking for units of seconds. So if we come in here and say that on our 25th frame, 25 minus 1 divided by FPS, this is when our particles will start. So as we scrub through here, you can see on frame 25 our particles start. Okay. But let's say that we want to go a little bit further. Let's say that if we're in here like this, we've got our cameras cut in nice and close. We may say that once this thing leaves camera, there's no need to continue to generate more particles. So on frame 43, for example, we'll just stop generating new particles. And so we can do that in here with another simple expression. We can go over to birth, and right now we've got this constant activation is turned on. So we can use a simple comparison. So $F is less than 44. So as long as the frame is less than 44, it'll turn on. So at frame 44 it turns off. And no new particles will be generated. So we've got this thing comes down and just emits some particles. So that's a very quick way that you can do this. You could as easily do this stuff with keyframe animation, but I find that personally it can be very nice to just work with the numbers directly in there, that you can type whichever frame you want rather than having to open up your channel editor and adjust stuff with the curve. And so the last thing that we'll want to do here is we just want to be able to cache out this simulation to disk. So if we come back up to the top level, we can put down a file node. We'll just need to save our file. So if we go up here to save as, we can put this in our desktop under test files, and FPS, and FF. Let's call this. So we can save, and under File, we can, instead of reading files, we can write files, but let's just choose a directory first. We'll just go to $hip/bgo/ $f. And right now I can't read this file, but that's because we haven't cached it to disk. And let's actually just quickly add some frame padding in here. And then we can write the stuff to disk. So go back to frame 1, write, play, and we can now read these files. And you can see that it has saved this to disk. It uses the $F3. So we've always got these the 3 digits. And we'll just accept, and there we have it. There's a very simple example of using some of these Playbar expressions. Hi there, and welcome back. We've been discussing global variables up until this point. So in the help docs here, you can see that we've got the expressions /_globals, and that'll take you to this page here. Global variables are available pretty much in all contexts. But now we're going to start discussing standard variables, which is where we really start getting into the meat of variables. They're commonly used and may be available between multiple contexts, but not necessarily all. But it's data that's very easy to lock down and use. So if we search for standard variables, let's get a sense of what they are. So if we search for this, the first thing that comes up will be the standard variables. And so we've got plenty of stuff such as the point position, the centroids, bounding box information. We've got primitive point numbers and primitive numbers. We've got some various ones that are used with particles such as life, or UV information, velocities, color. So there's lots of very standard stuff that's going to be used very frequently. And so it's going to be very useful to familiarize yourself with what some of these do. So what we're going to start doing is looking at a simple effect of taking a piece of geometry and blowing it apart. And we can do that using a number of very useful variables. So what we can do here is, within Houdini, we can just start by putting down a simple torus. And I'm going to just improve the quality of this a little bit. We'll just quickly go up here and add 20 rows and 20 columns. And this will give us a bit more detail here. I'm also, for the time being, going to just come up here and tell this to be hidden line invisible. Or even hidden line ghost. Okay, so we've got this torus here, and the effect that we're going to do is take each of these primitives and one by one kind of blow these off of the torus. So first of all, let's just add some color into this. So if we put down a point sop, PointSop is going to be one of the most useful tools for you in Houdini. This is where you'll be able to access a lot of your standard variables. You can see the normals and texture and color and stuff here, our point positions. And you can see that by default these all come with the variable mappings already put down by default, so that whatever feeds into it, it will continue to use. So what we're going to do now is we're going to use the bounding box to add some color information onto this. So you can see right here that this made everything a white color. And so I tend to prefer using one of these two modes here because it allows us to get into a fairly cheap wireframe mode where it's nice and quick in the viewport. But you can also, of course, use the various options, the flat shaded or the smooth shaded, and probably get a better sense of what the colors are here. So if we leave it as a smooth wire shaded, I guess, for now, we can turn this on, and as we start adjusting this, we'll get to really see the effect that it has. So what we're going to do now is change CR to BBX. And so you can see that along the x-axis, it goes in and it gives us bounding box information, so that on the minimum end of the bounding box we get a value of 0, and on the maximum end we get a value of 1. And that can be a little bit easier to see if we come in here and delete these other two channels for CB and CG. So you can see that it goes from black to red. We can again add the same thing in here, BBY, and this will give us blue values from 0 to 1. And we can do the same with green as well, BBZ. And so now we've got this rainbow-like shader or color associated with our torus. And so these are generated in point attributes. We can come up here, change this to details view, and you can see, get a sense of what the attributes are. You can middle mouse button here to see specifically what attributes are added on here, and you can see we've got a CD attribute. CD is up here, and of course the point position is going to be a default one. So you can see quite clearly that these values change over time. So now that we've got an attribute on here, let's just keep moving forward. We're going to add some normals on here. By default there's no point normals on, but when we add point normals, it allows us to get normal information on each one of these points, which is going to become useful later down the road, because as I said, we're going to start blowing away these these primitives, and that's going to allow us to, even though these things are separated, maintain a fairly nice shading on it. So we'll just leave this as is. We'll just add the normals and leave it. And now we can facet. And if we put down a facet SOP, what this will do is we can unique the points. And visually nothing just happened in the viewport. However, if we turn on our point number display, we can see that we have just increased the number of points here. And what this facet does is it literally just separates each polygon into its own face, which is part of the reason that we needed to add normals on here. If we go back to smooth shaded, if we disable our normals, you can see that this really gives us a very harsh edges here once we facet, because everything is suddenly disconnected. But by adding normals back in, it helps smooth stuff out. So we will continue to move along here. Actually, you can also notice that we've got the point normals are displayable once we add them in, simply by toggling over here. So we'll move on, and we're going to start breaking this thing apart further. Now, one thing to be aware of is that whenever you download files from on the forums and stuff, you'll probably see that a lot of our older users tend to use attributes such as color and alpha for a whole variety of things that you may not necessarily think of to use them at first. And that's because these attributes are very easy to access through a point SOP. And the key thing to keep in mind when working with variables is that even though they may be called color and alpha, you can really use any piece of data in Houdini to do anything. So a lot of the time you'll see people do stuff with color because it's just an easily accessible vector, or alpha because it's an easily accessible float. And so what we're going to do in this particular case is we're going to assign an alpha value, but we're not using this for transparency. We are using this for our own purpose. So add alpha, and we'll just turn off the display of transparency up here. We can come up to the miscellaneous, and we can turn off transparency so that we're not seeing any of that up here. Now what we're going to do here is, instead of using alpha, we're going to tell it to use the primitive number, $PR. You can see that value if you turn on primitive display here, and you can see that each of these is going to have a number. So what we've effectively done is we've created an attribute for each point connected to a primitive that has a value equal to whatever that primitive is. So this primitive is 317, and each of the 4 points are going to have a number associated that is 317. We can illustrate that further. We can go into Details View and click up here to sort stuff. And if we click here on alpha, you'll see that there's groups of 4 points all have the same number associated with them. And so that we'll have a use for that coming up here in a moment. So we've got these values here. And actually we can go one step further in illustrating this, and we can actually display this value in the viewport here. So if we press D, we can bring up our display again, go to Guides and Markers, and we can display a new custom attribute. So we'll create attribute text, turn it on, and right now we don't know what this is associated with, but we can right click on this and click Edit, and right now it's displaying our normals, but we can also tell it to display our alpha. And so this is where you will start to see that we've got 336, and we've also got all the points in the corners have 336 associated with it. They're also going to have other numbers in here because there's 4 points here. So that you can use this to the display menu to display some custom attributes as well. So moving along, what we're going to do now is, now that we've got this attribute on here, we're going to scale each primitive in. So we'll use a primitive sub to do that. And so if we turn on Do Transformation, we can see that we've got this $CEX, $CEY, $CEZ that comes up here, and that's looking at the centroid of each primitive. So if we middle mouse button on here and start scaling this in, you can see that each primitive will scale into its centroid. So we'll scale in everything to 0. And now if we turn on our point display, this has our number, but sorry, if we turn on our custom display here, then you'll see that each series of points here all have these same values, which coincide with the primitive number that we had here. So it can be useful to visualize this stuff. So we've now got all our points moved to the center of the primitive that they're associated with, and we can now fuse these together. Fuse. And that by default has gotten rid of absolutely everything because we have this remove degenerate option turned on. If we turn that off, you'll see that what's happened is now all of these points have fused together whenever they're overlapping each other. So you can see here, if we middle mouse button, we have 1600 points, whereas down here we now have 400 points. 1 point for all of the original primitives that we had. What we can do now is these point numbers that we have are not coincided at all with the primitive numbers, which is why we needed to sort this stuff using the alpha attribute. So what we can do is we can sort these because we want each point number and primitive number to be the same. So if we do that, we can put down a sort. And we can do this based on an expression, which we will say is $CA. And so now you can see that we have our primitive numbers and our point numbers are the same. We've got number 2 here, and again we've got number 2 here. So these points are now sorted very nicely. I'll just press L and move these over a little. So now that we have these points, we can start doing some animation on these, and what we can then do is use whatever animation we do to these points to drive our original polygons. So, for example, we can put down a particle SOP. And we can do some animation using this. Right now this is going to be birthing particles, which is not what we want it to do. We want it to manipulate our original particles. So under behavior, instead of particle system, we can have this say modify source geometry. And right now nothing's happening because we haven't told it to really do anything. So under forces, we can now change this so that it's got some turbulence. So if we say 17, 17, 17 for turbulence, we can increase the period as well. And as we press play, we'll now start to see all our particles will start moving around. And we can get this nice effect here of everything blowing apart. And so now comes the part where we want to suddenly use these points to drive our original polygons up here. So we can actually use another primitive SOP to do that. So if you middle click up here, put down a primitive, and wire the second input up here. If you middle mouse button on here, whenever you have multiple inputs on a node, you can middle mouse button to see what type of stuff it's expecting. And here it was expecting our particle source. You can do collision planes and forces and whatnot. On a primitive SOP, it's looking for our primitives and our template. So we can turn this on, and then we want to turn on transformations again, and we want it to rotate to our template. So we can just turn that on. And there we go. So we've got this simple effect here where whatever animation we've got going on to these points will drive primitives up here. And so that's why it was very important that we had all these points up here sorted correctly, is because we want it to be able to control specifically which primitive is moving. If there's a point here that's called point 1, that will affect primitive 1 over here. And so there we go. We press play, and we've got this thing will blow apart. And because we've got the normals added up here, it will all shade fairly nicely. And again, we've got the color controlled up here as well. So our primitives will all maintain their color as they animate through space. Now before we go any further, I just want to discuss the concept of attributes within the context of volumes. Now the variables that we've been using here, oftentimes you'll see these ones when you middle mouse button on a node, you'll see that we've got 2 point attributes. We've got CD and we've got N. Now those were added back up here when we created the point node. If we come up here, we see that we've got many other attributes. We've got CD, N, but then we've also got our alpha one that we created. We've got velocity, p-state, and life, because these are created by the particle network. These are variables which you can access using variables, but they're also attributes which get passed along on the surface and are very, very useful for a variety of things. Now, when working with volumes, it's a little bit different because each volume in itself is kind of a visualization of an attribute. So let's take a look at what we mean by that. If we middle mouse button over here and put down an ISO offset, we can use this to get a volume representation of a node. We can turn this to fog volume. And right now, we were previously just in our hidden line ghost mode, and so we want to switch this over to smooth shaded. And again, this is going to kind of look odd to us because we've previously turned off our transparency. So those are a couple things you need to be aware of when working with volumes. You can turn on the transparency, and now this looks nice again. So we'll just crank up the quality here. And you can see that by using this ISO offset, we've created a volume primitive, which looks like this in the viewport. And essentially, right now, we are looking at a float volume, just a single volume. And this is commonly, you would associate this with your density, which is somewhat similar to alpha. If we want to get color information in here, we can do that too. We can branch off here and use a volume mix. And one thing to be aware of is that, in particular, the bounding box information, we use that over here as $bbx, bby, bbz. When using volumes, we don't need to use the bb part. So we can use a user value over here on the volume mix. $v is going to be our incoming volume amount, but we can just change this to x, and we can write our own volume here. We can do this again using y and z. And then we can merge these 4 volumes together. So we've basically got this, which is our float representation. And actually, if I disconnect this for a moment, we also have this, which is a vector volume, basically. It's got 3 sets of information coming in here. So again, I'll just wire up the our original ISO offset here. And what we need to do now is associate names with these things. So we can use a name, and this way we can actually start figuring out specifically what this stuff is. So we'll just quickly add 4, sorry, we don't want any renames. I'll add 4 namings up here. So our first primitive is going to be called density. Our next one will be called CDX. Our next one will be CDY, and our next one will be CDZ. And these basically are our RGB channels. X, Y, Z, in this particular case, are RGB. And so we can put down a visibility SOP, is one way to do this. And we can say that our we want to hide everything except our first one, which is our density. And this allows us to simply come in here and view just our density, but we also have these other primitives down here, which if you come up here to the details view, under primitives, you can see specifically the name that's associated with each of these primitives. So it's very important to keep this in mind when working with volumes, especially when you're working with fluid simulations, because a lot of this stuff, like rest and velocity and temperature and whatnot, is all going to get created for you, but it's important to kind of have this background knowledge so that you understand what this stuff is and you can continue to work with it on your own. In Houdini 10, we've got the new Pyro Shader. If we go to the SOP context, Vex, Pyro, and this is going to be meant to use specifically with the Pyro effect stuff that we've got up here. So if you go into the Pyro stuff here, you'll be able to wire up whatever fields and stuff that you want. You can use, again, over here, you can create your own custom stuff and bring in whichever stuff you happen to create. So it's a very open system. And we're not particularly going to discuss any more stuff to do with volumes because it starts getting pretty complex and it's really a world of its own. If you are more interested in learning about volumes, if you go to the Side Effects website, you can go to Learning Tutorials, and we've got this Intro to Pyro Effects tutorial that recently has been released. And if you go under Dynamics, we've also got the Introduction to Fluid Dynamics in Houdini series, which reviewing the two of these and various other stuff on the masterclass on Fire and whatnot, you'll really start getting a better understanding of volumes and how they work. And so if we go back to Houdini now, you can take a look not at the Pyro Shader, but under the Material Palette, if you put down a basic smoke, we can see that we've got this Use Point Color option. And if we use that, what we can do with that is, remember these volumes that we created already, our RGB or XYZ, we are able to use these as our color attributes in our shader. So if we come up to the object level, I'll just quickly put down a camera and make sure that we assign that material to the object, basic smoke. When we render this, View Mantra, you will see that it's able to use that shader that we created, the smoke shader, and take those color attributes that we have also created and use that to affect the look of our render. So, as I said, variables are very, very useful, attributes are very, very useful, and you can do all sorts of things with them and drive all sorts of effects in your workflow. So next we're going to move on and we'll start discussing how some of these can be used in the context of particles. We're going to continue working with some standard variables. This time we're going to look mostly at ones that are available in the particle context and geometry context, and we're also going to take a brief look at the concept of groups, which are an incredibly useful function within Houdini. So let's just quickly start a particle simulation here. We're going to create a grid, and we're just going to raise this up a little bit and we'll source some particles from it. So source from geometry, and this is going to give us some particles that are kind of just going in every which way, and they're being generated from the points on the grid. So let's change that instead of from random points to random surfaces, and we'll take our birth rate down to something much lower, like 5. So you can see that we're birthing much fewer particles now. What we can do here is go to the Attributes tab and just take notice that we're adding to inherited velocity, which means we are inheriting velocity. Problem is, at this time, we don't actually have any velocity to inherit. So if you want, you can go up one level, and you can see that what this did was it created an object merge. It brings in our grid, I'm just going to hide other objects, and it ran that through a particle simulation, birthed some particles. What we may want to do, or what may happen for you automatically sometimes, is if you're doing a dynamic simulation of like boulders crashing onto your ground and whatnot, you'll a lot of the time get a velocity attribute for free. But you can also generate velocity attributes on your own, either with a trail sop or with a point sop. If you come over to here to the particle tab on the point sop, you see this section here that says keep velocity. If we change that to add, we can delete the channels and give this an initial velocity of 9.8. And so now when we press play, you can see that the particles will go down in this negative 9.8 velocity. So it's a very useful feature to be able to inherit velocities like that. But right now we're just going to keep stuff a little bit more simple, and we'll just ignore this for now. And we'll just work with forces and whatnot directly here in the particle context. So one thing that we may want to do is just change our initial velocity a little bit, and we can just set an initial velocity to 0. And you can see that nothing happens right now, which is fine. We can come back to the birth tab, and there's two more things that we want to do here just before we start moving on any further. The first one is we don't want these particles to die, so we'll just add an extremely long lifespan on here, something like 1 million. And we can also come in here to the birth probability, or sorry, to the birth group, and we'll just tell all of these particles that are ever created to go into a group called original. So as I started to say earlier, groups become very, very useful. And by putting these into a group and preserving these groups, we can now tell every particle that's born to access this group, which we can then do specific things to this. And it starts getting very useful once you have other stuff happening in your network, because you may have one set of particles that you want to do one thing to, but another set of particles that you want to do something else to. So let's start taking a look at that. If we come up to the drive particles, we can use a gravity node and tell these particles to start falling. So we get that, and now we want to start getting these to collide with the ground plane. So if we put down a grid, let's just scale this up to 15 maybe, and we can also turn the rows and columns up to 20, and then 20 by 20. So we can see that we've got a little bit of extra detail on our ground plane. What we can do now is come in here and add some add a collision plane. So we can select the particles, click collision, select the particles, press enter, and then select your object and press enter again. And so now in our particle network, it's come in here for us, and it does some collision stuff for us. What we're going to do instead of just letting it bounce like this, though, is we're going to get a little bit more fine-tuned control on this. We are going to tell this to die on collision, so that when all these particles come down, they just die. And we're going to birth new particles by using a split pop. So if we come back to the create particles, we can split our particles, split, and we want to split a group that we forgot to create. Over here on the collision tab, you can see that, or on the collision node, we get the same sort of options as we did over on the source. We can create groups. So let's just create a group here called collide. Now if we go back to the split, we can tell that only the particles that get added into that group will collide. Or sorry, will split. And so now we can see that we are essentially getting the same type of behavior as before, but it's a little bit more intelligent because we've got this new group of particles that it's actually getting born, that we can do specific things to these that will have different behavior than these. For example, we can come in here and birth more than just one point per particle. So let's set this to something like 5 to 10. And we can also come over to the attributes, and instead of simply inheriting the velocity, we can set an initial velocity. And if we leave it at the default here, they'll just kind of go in every which way. We can instead, though, start to use the velocity attribute. If you middle mouse button on here, you can see that we've got our velocity, acceleration, life, p-state, ID, and parent. What we can do is use our velocity attribute, the v, $vx, $vy, $vz. And we'll just leave the variance. And so you can see that this stuff kind of comes down, falls, and splits into a whole bunch of new particles. If we want, we can set a negative value on this $vy, and then we start getting stuff bouncing in the opposite direction. What we may want to do now is very simply put this gravity node here and rearrange this just so that it acts on everything. So let's just shake that off and put it over here. And you can see that that didn't really work for us. The reason for that is because whenever we use the split pop, you're seeing that we've got this dotted line here, and stuff that's happening in this chain isn't necessarily going to affect every other set of particles that's up here. So generally, what you may want to do instead is collect your particles together. We can collect this. We can collect these together and wire this up down here. And now you can see that we're getting the type of behavior that we were expecting. There was, for some reason, a little bit of a warning there. All I had to do was copy and paste the node, and it was working fine, so there's nothing to worry about there. So anyway, as I said, now we've got this gravity node behaving on everything, because we're telling it to act on both this set of particles and this set of particles. So now that we've got that happening, we can scale this back a little bit more. For example, we may only want this to go up by 0.5 of our velocity. Don't bounce at it entirely the same amount. And so you can fine-tune that. Furthermore, we will start adding some more behavior into this. And that is mainly that as these particles are born, we actually want them to die off too. So we can come over the birth tab and set their life expectancy much lower, maybe something like 2 and 0.5. And even that may be a little bit too high. Let's just change it to 1 second. And so this stuff will kind of die off there, 1.5. So it's always going to be about tweaking it to get exactly the look that you want. So some of these will die off before they hit the ground, but some of them will continue down past the ground. And that's because everything that the only ones that are going to collide at the moment are these original ones. So again, it may be useful to just create a new birth group called split. And by doing that, we can easily just copy and paste this, bring it down here, and what we can do is just tell this is to affect only our split particles. And this should be working how we need it to. Sometimes you may need to turn up your collision tolerance, or even if you go up here, you may need to turn up the oversampling to make this a little bit more accurate. And actually, if you press play here, you'll still see that even though it's got the oversampling up, it's not really fixing. And that's because I did something that is very easy to do. And if you notice here when we're splitting, we've got this preserve group option, which I enabled when we were doing this, but I didn't enable when we were doing the split. And what that means is that the only time that any particles will go into this group is on the moment that they're born. So you can see that on the previous frame it had 7, and in this frame there's 0. If you want these points to always stay in the group, you have to preserve the group. And that way you can properly do what you want with them down the road. Okay? So we've basically done our particle simulation as far as we need to take it. Let's go back up to the geometry level and start doing a little bit more with it. Okay, so if we go up here, we're just going to start doing some simple copy stamping onto here. So I'm just going to create a sphere, tab, sphere. I'm going to turn this into a polygon mesh, which means that if we view this in wireframe mode, it's going to look like this. Actually, let me just change it to polygon instead so that we get a little bit of a different topology. Turn the frequency up a little higher. And I'm going to put down a mountain node, which is going to make this look a little bit more cratery. And we'll just leave it like this. And the point of this is just to show that we can easily copy geometry onto our particles. So if we use a copy, you can see that we get this geometry will come down. And it kind of transforms in whatever direction our particles are moving in. It'll use the velocity as its axis to copy that onto. So we can simply do that, and there's a couple of different ways that we can control, I guess, our scale of our rocks. Right now, obviously, if you're new to Houdini, the way that you may want to do it is by controlling it here, but that's a little bit limited, and it can be better to do it using attributes instead. So let's try doing that. If we put down a point node over here, let's go over to the particle tab, and we can scroll down until we see scale. If we add scale, we can very easily start scaling our things over here. This can serve all sorts of uses, mainly because we can have a slightly different scale per point. So let's just put in a random function in here. We'll use a rand function, and we'll say that we want these things to have a slightly different scale depending on which particle it is. So $ID. Random by default is going to return a value between 0 and 1 based on whatever is inside the brackets. ID is a unique number that's associated with each particle. So if you middle mouse button on here, you see that we get this ID attribute down here. And if we come up here to the details view, you can see that that is a unique number per point. So very handy, especially when you start doing stuff like this where you can add a random scale to stuff, because you can see that this stuff will all get different values associated with it. For now, I'm just going to, I guess, copy this, and we'll just leave this at a flat value of 0.2 or something, 0.3. And we'll do some other stuff with this now. Something else that we may wish to do, depending on the effect that you're doing, is start adjusting the alpha channels. And we were taking a look at that before, let's just quickly add some color onto this first, actually. We can put down another point node. It's of course very possible to do multiple operations using a single point node, but generally I prefer to do it in multiple nodes because you can label this and say specifically that this is going to be point scale, whereas this is going to be point color. And let's just add a random some random color here. So the same way that you can easily control all this stuff scale, you can start doing that with color as well, or any other attribute. So we'll just add this random function in, like so. Now the problem with this is these all have the exact same color. The reason for that is because if you middle mouse button over here on the copy node, you'll see that we're not actually passing any of our attributes over. The copy node expects a scale attribute and knows how to interpret that, but it doesn't necessarily know how to interpret everything. If you come over to the attribute tab on the copy SOP, we just want to use template point attributes. So as you turn that on, you now see that as these things fall down, they've got random colors. Right now they've all got random grayscale values because our R, G, and B channels are always going to be identical. This rand function is not completely random, but pseudo-random, meaning that as long as you put the same seed inside here, in our case $ID, it will always return the same value. So if you want a little bit of extra randomness, you might just want to add a little bit of a random seed of your own. In this case, I'm just adding a completely arbitrary value. And in the end, you can see that we now get completely different colors on our RGB channels. I'm just going to leave that as is. But one other effect, as I started to mention, that you'll usually do with particles is control its alpha channel. So let's do that now. If we put down another point, we can add an alpha channel. And what you'll see happens here is by default we've got this alpha channel of 1, but you can easily start tweaking this down so that stuff fades off as it dies. And that's exactly what we want to do, is instead of having this stuff die, just pop off in midair, we want it to kind of disappear. So let's do that. We can add a new random function, or sorry, not a random function, but a new little bit of an expression that uses our life attribute. And our life attribute down here is, we were setting that with the lifespan of our nodes, and it kind of gives us a sense of it's a percentage of how long our particle should live. So it'll always be a value of 0 to 1 when you use $life. So it'll start at the beginning of its life, it'll have a value of 0, and as it gets older, it'll get a value of 1. We want kind of the opposite of that in this case, though. So you can just take 1 minus life, and now the stuff will all get born, but then as it dies, it'll fade off and disappear. And so it'll be a little bit of a nice gradual effect. And it of course looks better when you render than when you're looking at it here in the viewport. So that's it for this tutorial. We've covered velocity, ID, p-scale, life, and groups, all of which are very important topics. So keep in mind all the sorts of stuff that you can start to do with this information. And next we're going to start discussing local variables. Now, if we continue along the line of thinking from the previous tutorial, we were looking at the use of variables in the context of the dynamics, and in particular how you can use variables created at the geometry level to manipulate stuff in the dynamics. Now, we previously had looked at the volume shader and how you can use the various color attributes in your shader. And the same is obviously true with all sorts of geometry. So let's just quickly put down a grid here. If we dive in here and put down a color, we can color this grid. Let's just color it red. And we're going to assign a constant material to this. Constant. Now, we've got these options on here, tint with point color and use point alpha. If we go into these nodes, first of all, let's just do a quick render here. And we'll see that that grid, it renders red. And that's because we haven't tweaked anything in the shader, but we have that color attribute on here, which obviously must be getting used somehow in the shader. So let's just take a look at that. Inside the shader is the world of VOPs. If you're not particularly familiar with VOPs, it's a very powerful part of Houdini where you can start to do lots of work with the data itself, a lot of mathematical type stuff. Now, anytime you open up one of these materials in Houdini, you're going to see a whole slew of different nodes here. And the general color code that we've worked up here is that these gray ones are just general operations. The green is export stuff that's really specific to Mantra and when you're rendering. The yellow is going to be various parameter nodes that get promoted up to the top of the material. And these purple ones are looking for attributes from your geometry. So in the case here, you see that this is looking for our alpha attribute, this one is looking for CD, and this one is looking for UV information. It's actually a subnet, you can go in there and look at that a little bit further. But that's basically all there is to it in VOPs, is whenever you want to pass an attribute up, you simply need to create a parameter node. And that's all this is a parameter. It's the exact same as these ones here that get used up at the top. And because they're parameters, they will accept information. It can be strings or colors or floats or whatnot. If an attribute exists on your geometry that has an identical parameter name to a parameter that you have in the VOP context, your VOP will be overwritten with whatever those values are. And so that's how we are able to get our CD values or our alpha values or our UV values. And so that's why these nodes are just invisible. We don't want to be able to tweak these because we're using them with the intent of grabbing stuff from our geometry. So let's look at that a little bit further, because VOPs doesn't solely come into use when doing shading, but it can also be used for geometry level operations as well. So let's go back to our object, our grid, and let's quickly put down some UVs. I'm just going to get rid of this color. I'll do a UV project. Negate this. And so that's basically all we need to do right now. It's just a grid with UVs. What we're going to do now is scatter points on here, because we're going to just do a very simple particle simulation. So I'm scattering points, and we will just start off with 50,000 points, let's say. And if we look at that in the viewport, we've just got all these points scattered over the grid. And the beauty of using a scatter is that it will take any point attributes that exist on your surface and promote those up onto your new points. So we're already getting our UVs transferred up here. That can come in handy later. What we want to do now is just a simple particle simulation. So we'll put down a pop net. And we can dive inside and take a look at that. We need to put down a source, and we want it to come from the first context geometry, ordered points. And now it's time to just birth some initial particles. What we want to do in this case is we want to birth the same number of points that exist on our surface. So there's a local variable that we can use to get that, and that's $npt. $npt will look at however many points are feeding in to the previous node, or from the previous node, and it'll put that value down here. So we get 50,000 points. If we were to simulate right now, however, we're going to get 50,000 points every sub-step during this simulation, which can get out of hand pretty fast. So we'll just quickly put a nice little expression up here so that we only get particles emitted on our first sub-step. If our floating frame, which we learned about in one of the first tutorials, if our floating frame is equal to 1, then emit, otherwise don't emit. And you'll see that on frame 2 that we stop emitting. Okay? And so let's continue just a little bit further on here. We're going to set an initial velocity of 5 in the up direction with maybe a little bit of variation on here, so that we get these particles will just go off in this spray like so. We might also want to add some turbulence into this, so let's just do that using a wind dot, or pop rather. Wind, put that down, and we can just make sure that we push up in the Y direction, and we'll add a little bit of noise as well. So our seed, we'll just leave that for now. Roughness, we might crank that up 668. Exponent 0.712, and I mean these are really going to be tailored to specifically whatever type of an effect you want. You can see that it really doesn't have too drastic of an effect at all right now, and that's because we've still got no amplitude, and so let's crank that up. We'll set this to 44. So we've got some amplitude on there, but we can still use a little bit more refinement in here as well. So let's add a little bit of a lower frequency. And we can also just add a seed up here, so our noise will change every frame. And let's actually just add an offset in here as well. We'll also add an offset in here of $FF. Okay, and the reason that we haven't been getting anything is I forgot to set the wind to the display flag to the correct node. So anyway, we've just got some wild noise here that's just happening now, which is fine for our purposes. We just want a bit of a randomness happening here anyway. So obviously, play around with your seed and offset and whatnot as much as you want, depending on what type of a look you're going for. And finally, we'll just add a little bit of drag in here, just to help prevent stuff from moving too wildly. So there we go, we've got some drag, and that helps make this look a little bit more natural. So that's all that we're going to do here. Actually, I take that back. Let's just do one last thing. We forgot to add any sort of a life expectancy onto here. So if we come back to our source geometry under our birth tab, we're just going to want to make sure that we add a life expectancy. So we'll let our particles live for a second, but they could live for as much as, we can add some variance of 0.9, so they'll live anywhere between 0.1 and 1.9 seconds. So now if we press play, we see that the particles, they die off, so it's probably better to try to keep that in real-time mode. So there we go. Let's go back up to the geometry level, and now let's just do some quick, a quick VOP network on this. I tend to prefer to add stuff like color or alpha or whatnot to particles after the fact whenever possible during a simulation, because it allows you to cache at the simulation and just do tweaks at the geometry level, and you don't have to worry about redoing your simulation to make changes. So if we put down a Voxhop, we can actually do some work on the particles after the fact, after they've been simulated. So let's do that. We can put down a cache to do a temporary cache of our particles. We only need 120 frames here, and let's reload the cache. And so now we can just scrub through here. So now if we want to move forward, what we're going to do in this VOP network is we're going to assign a texture map onto our particles, because they've already got UVs, and then we're also going to add some an alpha attribute based on the lifespan of our particles. So let's dive in here. There's a couple of different ways that we can use attributes within the VOP context. I already mentioned before that you can do it using parameter nodes, but when you're in the geometry level, it's probably a little bit better if you don't do it that way. So let's just first look at the color. If we want to get the UVs in here, we can tab and import attribute. And then all we need to do is just simply tell it what the attribute is we're looking for. So in this case, we're looking for UV, and this will bring in our UV data. What we can do now is we can put down a vector to float, and this is because we need to be able to access specifically U and V, which are two separate float parameters, or attributes. Now we're going to put down a color map, and we can plug in U, and we can plug in V, and we can plug the color over here into CD. You can see by default we've got this mandrel.pick option on here, and that's why we've instantly got our color over here. We could also make this our default.pick if we wanted to have the butterfly image instead. So let's just go back to mandrel. And a nice thing that you can do with VOPs is when you want to create parameters, you can create a parameter node by simply middle-clicking and selecting the option. And so now what this does is it gives us a color map option that we can come up here and control that directly on our node up top here. So we can go back in, and now what we want to do is we want to use the lifespan of our particles and add an alpha attribute. We did that previously in the geometry context using a point SOP, but I'm going to do it here inside the VOP network for a couple of reasons. One, obviously, to just illustrate concepts, and another is because sometimes it's a little bit nicer to do stuff inside VOPs because you can actually make VOP networks multi-threaded. So we can change the number of threads. Instead of doing no threading, you can do as many threading as you have processors, so one thread per processor. And depending on how fast your computer is, this can be faster. So we'll just dive in here, and now we will look at our life attribute. When we looked at life before at the geometry level, we simply accessed it using the variable $life, because that is a standard variable that is kind of geared up nicely for you. It doesn't work quite the same way in VOPs. You can see here that we actually get age and life. If you come back up here and look at the details view, that's these two parameters here working together. We've got this, the life 0, which is the amount of time that our particles have been alive, and we've got this one, life 1, that tells us how long a particle is allowed to live before it dies. And so that's what the life and age is down here. So what we can do is divide the age by the life. I may have just explained that backwards, I can't quite remember. But life is the total lifespan, and age is how old the particle currently is. So that's why we divide it like that. Now what we can do is we can send that into a ramp parameter directly from here. And we can tell this to be a float ramp. You can of course give it whatever names and stuff you want, and that's how it'll appear up here. So we'll just leave it as is for now. And now if you want to create an attribute that does not already exist over here on the outputs, for example our alpha, you can use the add attribute to do that. So you can either create your own attributes from scratch, or obviously we want to create a pretty common attribute that is standard to Houdini. So we'll use add attribute, and we'll simply plug in this data here, which will automatically tell it what the signature is, whether it's float or whatnot. And our attribute is going to be alpha. And normally if you ever want to access alpha anywhere in the geometry context, the variable name for that is $CA. So we'll just fill that in so that it's standardized. And that's that. We are currently importing our UVs and adding colors, and we are also adding an alpha attribute. Vops will kind of process everything that goes on inside this node. So if we come up here, we can simply raise this parameter up here, and if we go over to the details view, you'll see that we now have our color and our alpha. And our alpha value will start off at a value of 1, and as the particles get older, the alpha value will diminish so that they fade off as they die. And so that's that. Again, attributes can be very useful, and this is just a bit of a demonstration on passing them into the VOP context. And so as you can see from this video here, this is what the rendered effect would look like if we were to render this sequence out. Alright. So we've been using variables for a whole variety of reasons right now, and I'm going to help drive home the idea of custom variables with So we've now got this big long expression that we need to figure out what it is that we can do with this. It's going to be very hard to visualize this, especially since it's so long, and depending on what you're doing, you may have even more numbers. So let's look at it in another way. We can go to the HScript text port, and this will open up our text port. We briefly looked at this in the last example. And if we do an xhelp, I'm not going to bother finishing the word details. I'm just going to finish by pressing enter. And it's going to give us some suggestions on what some options are for the xhelp. Now we've up to this point used detail, which looks at a float value. Float detail, and then your node, your attribute name, the index number. The problem is that this attribute that we've created is a string, not a float. So let's take a look instead at details. You can just highlight that, and Control C, xhelp, Control V, press enter, and this one is looking for a string, detail attribute S, the surface node, and the attribute. We can also use the echo command that we learned briefly in the previous lesson as well to examine that. Now, if you're not over familiar with the text port, This is actually Unix based, and our Houdini file itself is kind of like a file system. If we type ls, it'll list all the folders we have. So we can change directory into our obj directory, type ls again, and it lists all those nodes that we have. Currently we're in obj/tweaked water. So what we want to do is we want to echo the details of obj slash obj tweaked water slash null1. And we are looking at the goners attribute. Actually, let me get rid of that slash there. So if we press enter here, let me just complete the backtick over here. Let me just quickly take a look. We probably do need that slash. Actually, the problem is that this null1 node doesn't exist at all. It's the for each node that we want to look at. What I normally do is I'll put down another null, and let's actually just do that quickly. It's always good to have these placeholders here. So null. And one thing to make a note of is that the for each loop, this is inside geometry, and so this is going to calculate every frame. Depending on how many points you're processing, that may not be a good thing, so let's just lock this. And now it doesn't need to evaluate, it's just going to read this piece of information every frame. So we've got that locked down. Now let's go back to the text port, and let's try echoing this again. Only instead of null1, it's just going to be null. Okay, so now what we see here is it returns this ID == 7, and we can scroll all the way across and see all the values, and we can confirm that at the end the attribute ends in a nice expression value. It doesn't end in a trailing $ID ==. It ends nicely. So now that we know this, we know that we need the details attribute, or sorry, the details function, to be able to call this up. So let's just copy that. Sorry, we can select this and Control C. And now if we put down a new delete node, we'll wire this up to our original file sequence. And we can come in here. We want it to delete non-selected. We want it to delete points based on an expression. And this is the expression that we want it to delete. We can also just substitute this out for a local reference. So /null. And we get an error. If we middle mouse button on here, it says it's unable to evaluate expression, bad type for function or operation. It really does not like what we're trying to do here. What we need to be able to do is tell this filter expression to expect an expression from this and how to treat it. And for that, there's one last function that we'll be learning, eval. And so if we put an eval around this, it now understands that this is an expression and it needs to evaluate it. And that's that. We have basically accomplished our goal, except you can see that out of habit I used the delete non-selected, whereas we actually want to delete the selected. And so this was the original goal that we were going for. If we put our glass of water back in here, we can see that what we're getting is the glass of water fills up, and those stray particles that we have are deleted, and we basically are pretending that they don't exist. As I said at the very beginning, It's a little bit redundant for this particular example because we could have just blasted those, but the information that you need to pull from this four-part lesson is A, the usage of a for each node, how you can recursively go through stuff, how you can create string expressions in particular, or string attributes rather, and continuously overwrite these strings, particularly using the for each, to build up some complex expressions that you can then evaluate. So there's really no end to what you can accomplish when you start getting into functions. And while it may not have been particularly useful in this particular glass of water, if you're doing some very complex particle simulations where you've got, as I said, particles dying and birthing all the time, you won't be able to just use the blast because point numbers will be constantly updating and you'll have points disappearing and appearing randomly throughout your simulation. So if you want to delete more accurately, you should delete using $ID. And in that particular scenario, this type of a network will make that quite easily. You could save off this part of your file as an all-purpose tool, and just know that whatever you feed into it, you'll be able to cycle through and delete using the expression. So I hope that this has been beneficial. Personally, I find expressions to be an invaluable part of the workflow, and hopefully, like I said, this has been of benefit.